Hi, this is Dr. Xu teaching design of experiments for engineering research. In this video, I will show you how to present the data for the randomized complete block design and perform the data adequacy checking. We will use the same hardness test example dataset used in the last video. The dataset is shown here, as we will read it from an Excel file. Make sure you have installed the Read Excel package using this line of code. Firstly, I will show you how to create this box plot. It shows the strength variation for each different type of tips. The code is shown on this slide. I will also post it down below in the first comment. From the first line of code to here is what we have done in the last video for the ANOVA analysis for the randomized complete block design. The plotting of the box plot uses the last three lines. I will copy these lines of code to RStudio and execute them first. Now you see that the strength data frame stores all the data imported from Excel. With this line of code, I set the plot shape to square. The box plot is plotted by using this box plot function. The data in this function is the strength data frame, so it uses the data from here. The data for Y is the strength column here. And the data for X is the tip column here. The X label is tip type and the Y label is strength reading. Enter. Lastly, I give a title to this plot. Enter. Now you can see the title is shown here. This plot shows the strength test variation due to the use of 4 different tip types. One aspect we want to look at is the additivity of the randomized block model. The linear statistical model that we have used for the randomized block design is this equation. So basically we are saying the response Yij can be expressed by the 3 terms on the right plus the random error. The random error is the residue in the model. Mu is the grand mean, so it's the mean of all the data. Tau I is the ith treatment effect, and beta j is the jth block effect. What we are saying is that the response Yij can be predicted by using the overall mean plus the impact created by the treatment plus the impact created by the block, and there is a random error, which is the residue. This is the completely additive model with no interaction between the treatment and the block. Let me explain this by using real numbers. For the same strength test example, these are the strength test results for different tips in different blocks. So in total, we have 16 numbers. The grand average here is the average of these 16 numbers. The block averages here are average of the 4 numbers in each block. So this number is average of these 4 numbers, and this number is average of these 4 numbers. It's the same for these 2 numbers. The treatment averages here are the averages of the 4 numbers in each treatment. For example, 92.9 is the average of these 4 numbers, and 91.825 is the average of these 4 numbers. The block deviations are calculated by subtracting the grand average from each of these block averages. So 87.7 minus 89.75 equals to negative 2.05. This is the impact of block 1 to the response. It means on average, block 1 results in decrease of 2.05 from the grand average. The rest of the 3 block deviations are calculated the same way. The treatment deviations here are calculated by subtracting the grand average from each of the treatment averages. So 92.9 minus 89.75 equals to 3.15. This is the impact of tip 1 treatment to the response. It means on average, treatment 1 results in increase of 3.15 from the grand average. The rest of the 3 treatment averages are calculated the same way. Using this model, the predicted value can be calculated for each combination of the treatment and blocks. Let's predict the result for tip 1 and block 1 and put it here. It equals to the grand average 89.75 plus the treatment effect of 3.15 plus the block effect of negative 2.05, and the predicted value is 90.85. The rest of the predicted values are calculated similarly. The residue term here is calculated by subtracting the predicted value from the actual value. For example, 90.3 minus 90.85 equals to negative 0.55. If we look at tip 3 and block 3, 89.6 minus 89.275 equals to 0.325. Using the same method, all other residues can be calculated. This additivity assumption or no interaction assumption is crucial for block designs. We can plot the residues versus fitted data or predicted values to check the additivity assumption. The R code is listed here. We can copy this to RStudio and execute them. So we restore original graphical setting and set the plotting shape to be square. We plot the residues versus the fitted data. The residues should be evenly distributed on both sides of 0. And this plot shows no issue with the additivity assumption as it does not show any particular pattern. As what we have done before for the single factor experiment, it is also important to check the data adequacy for the randomized complete block design. The first plot, we use the run sequence plot to check data independence. This plot is created by using the test sequence data in the strength data frame as data for X and use the residues data of the ANOVA analysis as Y. From the plot, we don't see any specific patterns of the residues that violate the data independence assumption. Next, we will check the approximately normal assumption using the QQ plot. The QQ norm function plots the residues against the normal z-scores, and the QQ line function plots the red line for perfectly normally distributed data. As we can see, most of the data points in the middle area are either on or very close to the red line. This indicates that the data we have collected are approximately normally distributed. Also, we can use the standardized residue plot to check potential data outliers. As all the standardized residues are within -2 and +2, it does not point out any potential data outliers. The third condition is to check equal variance. We can use the strip chart function to plot the residues for each treatment. In our example is the tip type. As we can see, the spread of the residues are about the same, indicating equal variance for each tip type. We also want to look at the residue distribution for the block, so residues versus block. And in this example, it is the tested metal type. The variances of the residue also looks okay. By using these 3 lines of codes, we can plot the 4 plots here at the same time. This is the residues versus fitted values. This is the standardized residues versus fitted values. And this is the normal QQ plot. And the last one here is the standardized residue distribution for each level of the tip type factor. Alright, to conclude this video, we have talked about the ways to present the data for the randomized complete block design and to perform data adequacy checkings. Please leave a comment if you have any questions. Thank you very much for watching. If you feel this video is helpful, please subscribe, like, and share. This is Dr. Xu. I will see you in the next video.